Welcome. So let's continue our discussion on analytic functions. So the question is to determine whether there's at least one point in the complex plane where the function f of z given by z by conjugate of z is analytic. So we have to test whether z times its conjugate satisfies, or what conditions make z times its conjugate to satisfy the Cauchy-Riemann equations. If it's possible, then the values of x and y that will make that to be true will give us the points where the function is analytic. Solution. So let z be given by x plus iy, which means conjugate is x minus iy. So f of z given by z times its conjugate is given by this product. When you work out, you get x squared minus xyi plus xyi, I times I squared, which is -1 times negative y squared is positive y squared. So check that we'll have x squared plus y squared, and then say plus 0i. So this means that u of xy, the real part of f of z, is x squared plus y squared, and the imaginary part is 0. Now, partial u, partial x is given by 2x, partial u, partial y is given by 2y, partial v, partial x is 0, and partial v, partial y is also 0. Now, for Cauchy-Riemann equations to be satisfied, we need partial u, partial x to be partial v, partial y. So which means 2x should be 0, which implies x should be 0. And then partial u, partial y should be negative partial v, partial x. This means we expect 2y to be negative 0, yes, 0, which means y should be 0. So we say that the Cauchy-Riemann equations are satisfied only at the point x comma y, which is 0, 0. Therefore, w equals to f of z equals to z times conjugate of z is differentiable or analytic only at one point z equals to 0, and nowhere analytic that means not differentiable within the neighborhood of z equals to 0. Question 2. Is the function f of z equals to conjugate of z analytic? So to show that this function is analytic, we have just to show that it satisfies the Cauchy-Riemann equations. So solution, let z be x plus iy. So this means so then u of xy will be x, and the v of xy, the real imaginary part, is negative y. Now partial u, partial x is 1, partial u, partial y is 0, partial v, partial x is 0, and partial v, partial y is negative 1. So for f of z equals to conjugate of z to be analytic, it must satisfy the CRE, Cauchy-Riemann equation, i.e. partial u, partial x is the same as partial v, partial y. But you see partial u, partial x from our calculation is 1, which is not equal to partial v, partial y, whose solution is negative 1. So immediately any of the two equations is not satisfied, then the analyticity property fails. So since partial u, partial x is not equal to partial v, partial y, in this case, the function f of z equals to conjugate of z is nowhere analytic and nowhere differentiable. So the function is not analytic because Cauchy-Riemann's equation, especially the first case, is not satisfied. Question of the same nature before we stop. Is f of z given by 1 over z analytic? Now here, let z be x plus iy. This by definition. So this means 1 over z is 1 over x plus iy. So we can rationalize this. We have x minus iy, and then this is the x squared, and then plus y squared. So which means f of z is 1 over z x minus iy over x squared plus y squared. And then you can always separate real and imaginary, x over x squared plus y squared minus or plus negative y over x squared plus y squared I. so that u of xy is x over x squared plus y squared, and imaginary part v of xy is negative y over x squared plus y squared. So then now, to test the analyticity of the function, we have to show whether the function satisfies the Cauchy-Riemann equations. So partial u, partial x. Now we are going to use quotient rule. So let this one to be u, this one to be v. Quotient rule is u prime v minus v prime u over v squared. So u prime is 1. So we'll have 1 times x squared plus y squared minus v prime is 2x. And then x squared plus y squared squared, which will be x squared plus y squared minus 2x squared over x squared plus y squared squared. Now this will give us y squared minus x squared over x squared plus y squared squared. Next, partial u, partial y. So this is u and v. So u prime is 0 times x squared plus y squared minus v prime is 2y divided by the square of v. So which will be negative 2xy over x squared plus y squared squared. Now partial v, partial x. So remember v is negative y over x squared plus y squared. So u prime is 0 times x squared plus y squared minus v prime is 2x times minus y divided by x squared plus y squared square. Minus minus is plus, so 2xy over x squared plus y squared square. So that's partial v, partial x. And then lastly, partial v, partial y. U prime is minus 1 into x squared plus y squared minus v prime is 2y times minus y over x squared plus y squared square. We have negative x squared, negative y squared plus 2y squared over x squared plus y squared. This will give us y squared minus x squared over x squared plus y squared square. I hope you can see clearly that partial u, partial x is actually exactly the same as partial v, partial y, and partial u, partial y is negative of partial v, partial x. Clearly, partial u, partial x is partial v, partial y, and partial u, partial y is negative partial v, partial x. So which implies Cauchy-Riemann equations are satisfied. Also, partial derivatives are continuous except at the only point we have problem in this partial derivatives is when both x and y are 0, because we'll get 0 in the denominators. Therefore, f of z equals to 1 over z is analytic everywhere except at the point i.e. at the point z equals to 0. So that is how we show that, or how we test whether the function 1 over z is analytic or not. Thank you.